Para a segunda palestra de hoje, do João P. Ramos, e vai falar em inglês, né? Okay, so he will tell us about engineering uncertainty from Heisenberg's principle to shape optimization.
Yeah, thank you, Henrique, for the introduction. Yeah, it's definitely amazing to be here. So before I start my talk, maybe I should, talk a little bit about my career path so far, just like Pavel did. So I did my PhD in Germany, then I eventually did a postdoc here for 6 months. I did a postdoc in Switzerland for 4 years. I was for 6 months at the University of Lisbon, and then I arrived here last April. But I want to start by going back a little bit even before that, maybe to around 2012, 13, when I decided that I wanted to be a mathematician, right? So I came to IMPA for the first time in 2012 as a Math Olympiad student. I was taking some classes here. So Gugu was one of and Rob were two of the guys who were teaching me at the time. And when I set foot here, I was like, wow, this place is amazing. I really want to be part of this institute someday. So that is a happy ending for me as far as that's concerned. But I wanted to tell you guys a bit about this day. So this day, the 15th of August, which is when people told me that I needed to give a special lecture. They gave me two options, and this was by far like a trivial choice. And you guys are going to understand why in a bit. So why is that a trivial choice? When in 2012, I decided that I wanted to be a mathematician, many people were like, dude, so you want to be like a math teacher or something? They didn't really get, what I meant by I wanted to be a mathematician. But there was one guy who is an engineer that always told me, look, you seem to really like this math thing, so just do your thing. As long as you're happy, I'm happy. And as long as you're doing good to the world in general, then I'm happy. And today, 15th of August, is that engineer's birthday. So I wanted to start talking about this important engineer who actually 10 years ago was in IMPA. I found this picture on his Facebook yesterday. So he took a picture right next to the Brazilian Colloquium of Math banner. He was very happy at the time. So the captions, I didn't include it, but they read something like, did I become smart? No, not really. I just visited where my son is studying. So that is, so that guy always supported me throughout my career. But one thing that hasn't changed since around that time, since when I decided that I wanted to be a mathematician, is that he first and foremost, he started making this very silly joke that I kind of like, which is, he used to say that, an engineer is a mathematician with good common sense, with good judgment. So you isolate variables and you get that a mathematician is an engineer without good judgment. And that's what he said. And I thought that, with time, this dude, after I got my position, he would maybe come to the realization that it might not be so. But he actually made this joke a couple of months ago again. So I decided that, my inaugural talk, so the aim is showing that this is wrong, So let's strike that out. Instead, we're going to show that it holds if we swap signs, right? So I think that on his 70th birthday, the best thing to show is to show that he was wrong and he did like an engineering mistake, right? So just like swapping signs, harmless engineering mistake. So let's go about that. Okay? Okay, so what kind of thing do I want to talk to you today? So I want to talk about, since I said that it has to do with engineering, I want to talk about problems that come from engineering. And what are those problems? Well, those problems come from the field of signal processing, and they, in some way or another, they have to do with my field of study, which is harmonic analysis, more specifically Fourier analysis. That's where I'm a Fourier analyst by training, so I always try to work on problems that are related to Fourier analysis some way or another, right? So yeah, I have to explain to you guys what both of those things are. So, well, let's start with some basic setting the groundwork. So we just take it out to function, right? So a measurable function with nice properties. And this is what we're going to call our signal, right? And this is just like, kind of like a generic word for an object that's going to be relevant from, this kind of, from our problem's point of view. And what are some examples of things that we call signals? So for instance, like if you're working in the context of electrical engineering, and if you look at voltage as a function of time, then your signal might be exactly that. Just like you take like the time series of voltage of the intensity, and that's one function, that's your signal. You say that, well, that's my object of interest, I'll try to work with that. Another possibility is, well, for instance, if you're working in acoustics, and you want to kind of, as we're doing right now, I'm speaking into a microphone, the sound is coming out, and you guys are understanding. So we kind of want to render and have the sound come out as clearly as possible and with the highest quality as possible. And then the kind of variations in air pressure that the sound wave induces, well, this could be like our signal as well. So in the context of acoustics, these are going to be our signals. And finally, so for instance, in optics, if you want to project something like, this beamer is projecting at the moment, so this whole frame here, then, well, the light intensity at every point that is being projected on the wall, well, that's also a signal that induces a natural function. And of course, we can start analyzing those functions, right? And first, yeah, so that's all well and good. It's basic definitions. But then what do we want to do that? Well, in practical terms, sure, you might have a signal, but you might not have a lot of information on that signal, or you might have just a specific kind of information on a signal that you can measure. So the first common question to all of those and many more contexts is, well, how to encode information of a signal, right? So how do we make sense of the signal if sometimes we only have partial information? And maybe I should, since I'm talking about Fourier analysis, I should talk about this basic idea that dates back to Fourier. So Fourier said, well, what if we have a bunch of basic functions which just do this and do this more intensely the more you go deeper into your function set? Maybe we could, in a way, represent our function as a superposition of such waves. And this very basic idea actually gave rise to my whole field of study, right? So this is basically the idea of the Fourier transform, which says that, well, the Fourier transform is just this object here, which is that superposition of those waves. If you guys feel intimidated by that, don't. This is just saying, well, these are waves, so these are those functions that, as I said, are doing exactly this. And f is just our weight. It's saying how we're superposing those waves, right? And then we get this object, and by Fourier inversion, we can actually recover our original signal from this kind of measurements. We can write the function itself as a superposition of waves, right? But this, alas, has a very not useful property that, well, we need values of the Fourier transform at all points here if we want to recover a function f, right? So if we have a very generic function f, and we want to recover it from this kind of thing, we need all the values of the Fourier transform. So it's kind of like, the same amount of information. For some problems that might work, but in nature it's not really that common that problems like that, where you have all information in one side happen. Sometimes you have, most of the time, way more often than not, you have information on one side, so some physical information, some frequency information, and you want to make sense of your original signal from that, right? So then the second common question is, well, how do we optimally encode information of a signal, right? So that is basically what we are looking forward to do. So let's maybe take a look at a couple of alternatives for that. So the first attempt is through the Heisenberg uncertainty principle. So So many of you might know that from, I think, elementary, introductory undergrad physics or something. But I really like the Fourier analysis formulation of that, which basically says this. So it says that if I take any L2 function, any function whose square is integrable, its L2 norm, it's bounded from above by this constant here, times the L2 norm of f against this weight to the 1/2, times the same thing for the Fourier transform to the 1/2. And these two parameters are actually arbitrary, right? But then if we try to make sense of that, well, it's all well and good. I think you might say that's very cool. It's a very cool inequality. It's symmetric. It has a very explicit constant. But why is that useful for us? Well, let's suppose that f is supported on a very tiny interval of measure epsilon. Then this thing here is at most epsilon squared, right? Then you take it out of this integral, you get epsilon here. Suppose that f hat is supported on an interval of size delta, you get delta out. So here you get basically that this right-hand side is bounded by the L2 norm squared times 4 pi times epsilon times delta. So epsilon times delta, if this is too small, then the function cannot be identically zero. So in other words, if we have a signal, right, and we know some properties of it on physical space, we know it actually is very much, all the information of that signal is concentrated on a very tiny interval, and its Fourier transform the same holds, then the signal has to be zero. So in other words, if we know a signal outside of a tiny interval, and if we know it in frequency outside of a tiny interval, we know it completely, right? So that's basically our second consequence. And yeah, so let's maybe see what other results we can use to try to recover information on a signal from, you know, some space frequency data, right? So we start. So for instance, a way to do that is through the Paley-Wiener theorem. And for those who don't know, this theorem just says, well, suppose that if you take a function and this Fourier transform, that superposition of waves that we have, it's compactly supported on the interval minus 1/2, 1/2. Then something magical happens, and our function is determined by a discrete set, right? So we have that our functions, our signals, they're determined by just like sampling on finitely many points. And this actually allows us to do a lot, right? So we passed from the case where we needed information on the whole Fourier space for the case where we just need information on the physical space at a very sparse family of points. So this kind of allows us to do a lot, but unfortunately, again, not all functions are such that the Fourier transforms are compactly supported. And we're going to see that that is way more often than not the case. So maybe if you want to deal with more general functions, we should not rely so heavily on this function, right? As a general rule of thumb. Okay, but then there is, okay, so if you want to rely with more general functions, how about this? How about instead of interpolating on just one side, how about I collect information from both physical space and frequency space, right? And that is exactly what the Radchenko-Wiazowska interpolation formula, which is a result that it seems like it was proved 100 years ago from, you know, how pretty and elegant it is, but it was proved like 8 years ago by those two guys, so they're two good friends of mine. And this is one of my favorite results in Fourier analysis, and what it says is basically if you give me any function that is very nice, it decays nicely, and its Fourier transform is also very nice, then I can recover that explicitly by sampling at points of intensity root of n, where n is an integer, if I do the same also for the Fourier transform. And I can manage to recover it completely, right? But still, again, this comes together with a catch. And the catch is that, well, I said that I can recover the function. I didn't say it was simple to recover that function, right? So the interpolation basis is actually a nightmare. It's given by some Laplace transforms of quasi-holomorphic modular forms, actually, which are they're fun and cute to define, but for practical terms, they're not good, right? For practical terms, we need something that is more robust, that can allow us to run algorithms on it, so that can allow us to integrate on it, right? And so basically, in order to introduce that, I try to come up with as most story to tell, but I keep on falling back to the words of Karl-Heinz Gröschenegg, who is actually one of the pioneers in this area. So I decided to just quote his work. And Gröschenegg actually says that, well, if you think of f, the signal, is just describing like this. Let's think about this acoustic case, right? So the case of acoustics. That we're thinking of f as describing a piece of music. So if you take a look at f of x, this is describing basically how much, as I said, the dislocation of that the sound waves produce in the air, maybe through a speaker or something, and maybe this is describing like how much a membrane is vibrating with time, and so you can recover some stuff from this, right? So this in particular describes if you just have the signal f in the case of a music. We can describe like some rhythmical patterns, right? You're going to see like there's a spike whenever like the beat drops or something like that. But then you're not going to see, something that you're not going to see by looking at it is the key of f, how it sounds. Well, it's just not there. But then, if you look at the Fourier transform, this actually just says, well, what are actually the notes of your that are present, right? So the highest frequencies, so the dominating frequencies of your signal. But again, unfortunately, some things are lost, like the rhythmical patterns that we have before, we cannot see it anymore. And again, of course, the melody, how it sounds, is something that we don't have, right? But, well, actually, it seems that we're lost, right? So there is no way to do it. But actually what the ear does is actually take both of those things at the same time, mash them together, and give it to your brain and say, look, here is some way to interpret that. And you make sense of it. You make sense of what you're hearing by listening both to the highest frequencies of the sound, but also to what rhythmical patterns in time we have. And that is basically what a musical score represents, right? So if you take a look at a musical score, you're going to see like there's the notes, the musical notes that are like drawn on that score. They're just describing perfectly at each time what frequency is vibrating the highest in your song, and like describing exactly as well how much each of those notes is lasting for. So this is kind of the perfect decomposition in our terms, right? So this is kind of the mathematical object that we want to define. And in order to do that, well, it actually, it seems like from the introduction that I did here, that it's really hard, but it really isn't, right? So the idea is, well, we should just restrict both in space and frequency and see what happens, and maybe like hope for the best. So we start by restricting our signal in space to an interval. Okay, but maybe in frequency we don't have any information on that signal anymore. So now what do? Well, we take its Fourier transform and we restrict it as well to a different interval j. And we transform back. So basically, this is also known as the most naive thing you can think of, right? So you restrict in space, then you take Fourier transforms, then you restrict in frequency, and you transform back. You hope it works. And then you get an operator that looks more or less like this, right? So if you think of those intervals as translations of some fixed family of intervals, we can write that operator in this form here. So note that now, this might look weird, but it really is not. So what does that have that is useful for us? Well, it has a translation in terms of the physical space, so it's determining more or less where we live in physical space, and it has a frequency like those basic waves component that we were talking about before. So it is kind of like a localized version of the Fourier transform we were describing before. But then there's this annoying thing that x and s are not the same. So what do? Well, we just take x to be s because trying to define an operator, so maybe we should look, instead of looking at the hardest possible case where this translation parameter could be different than that, let's take them to be the same. And in that case, we obtain that the localization that we want has this exact shape. So it is given by f times this thing that looks like these basic waves, the Fourier transform, this exponential basis, times phi at t minus s, where phi is a given function that is determining where we're localizing in space. And this is exactly the definition of the operator that we're after. And that's exactly the operator that is used in practice as well. So this is, so for a fixed function g, which is in our previous case was this phi, the short time Fourier transform is the operator defined by, for each x in psi, I compute the short time Fourier transform at x psi by exactly this formula here. So what I'm effectively doing with this operation, we're going to see it in the next slide, it's, well, I have my signal here, and my function g is just like, it's telling me where we're localizing, and I'm sliding it across. And by sliding that across, I tell you, look, yeah, I want to focus on this part of the signal and then analyze that in frequency. So then I do that, I slide it across, I take Fourier transforms, and I get one vertical slice of this picture. And if I assemble all of that slice, all of those slices, it gives us a time frequency picture of our signal. So it gives us something like that decomposition that we wanted. It gives us something that says, look, our function is jointly on space and frequency behaving in a suitable form. Right? It's giving us like the sound that we want to hear. Okay, so that's all well and good, but I promised you guys that I was going to talk a bit about this operator so in a more harmonic analysis perspective, right? So since I did do harmonic analysis, we should look into that, and then we come to the next part of this talk, which is, it's how can we make sense of those operators and how can we make sense of them concentrating on certain subsets and related to different areas of mathematics, so such as harmonic analysis, complex analysis, and PDEs, and so on. All right, so we start with a naive question. So let's recall that we had this task of, we have this operator that describes our signals very nicely on space and frequency. And let's suppose now that we want to say, look, yeah, that's really cool, but I really want to know how much I can actually concentrate a signal on a fixed domain in this time frequency space, right? Suppose that we want to know, okay, maybe I have a certain window of time frequency data that I can measure with my device, and with that window of time frequency data, I want to recover my original function. I want to concentrate it on that domain as much as possible so that I can have as much useful information as possible. So then we naturally come to the question of, well, how can we, for a given, so we come to a couple of very natural questions, which are basically, well, for a given window G, how can we optimize these quantities? So either we could ask two questions basically. So either we stop F and we vary the domain U, or we stop U and we vary F. So what is the best signal that concentrates on a domain? What is the best domain for a given signal? And so on, right? So the thing is, there is a preliminary result that says that, well, there is limitations to how much I can concentrate. And that result is actually, it's this very basic weak conservative principle for this operator, the short time Fourier transform. And it says that if my window and my function have L2 norm equal to 1, then if this operator concentrates almost all of the mass, so this is, I forgot to say, but this is an isometry from L2 to L2, right? So if it concentrates almost all of the mass in this set U, then the measure of U is non-trivial, right? So I have my set cannot be, just like in this original asserted principle of Heisenberg, I cannot have a very tiny box in time frequency space that concentrates the whole thing. So although this time frequency picture that we built is better, still recursed by the uncertainty principle, right? And the proof of that is actually very simple as well. So it's just triangle inequality. We go back to the definition of this thing. We pass the absolute value inside. We do Cauchy-Schwarz. And we get that pointwise, this inequality holds by just Cauchy-Schwarz. So then, well, then the integral on the set U is less than, of course, 1 times the measure of U by this Cauchy-Schwarz, but we supposed it was 1 minus epsilon. So we get a trivial bound for the measure of U. And it says, okay, cool. Well, we have some estimates on the size of the set. And then the question is, well, yeah, maybe it could be, although this box U cannot be super small, maybe it could be the case that we could concentrate a signal or most of signals in a finite box, right? So it could be the case that we could take a signal, we could concentrate it all on like a ball or something like that. So the question is, well, how sharp is this previous result? So it just says that the measure of U has to be at least 1 minus epsilon. Could it be, for instance, 2? And the answer is actually it's not very sharp. So it gives us, so if we work a little bit harder, we get a different lower bound by Lieb's uncertainty principle. And if we optimize in P, we get something that says that the measure of U has to be at least 2 in the asymptotic limit. Okay, that's very cool, but still the question remains, can we concentrate still on a ball of radius, I don't know, 100 or something like that, of measure 100? And basically, the whole issue with that, and the reason why, the reason to believe that it shouldn't be possible is there's this result by Philippe Jamin, which actually says that, look, if I take 2 functions, f and g, that are in L2, then whenever that short time Fourier transform has compact support, then either my original function f, my original signal f, or my window has to vanish. So I'm in the trivial case. So this says that I cannot perfectly concentrate on a finite measure set unless I'm in the trivial case, right? It's still, the question remains of, can we almost perfectly concentrate on a domain? And therefore, in order to answer that question once and for all, let's try to analyze these quantities here, right? So this is kind of the quantity that we can that we care about. So how much we can concentrate a given signal in terms of its total L2 mass on a domain, and then we take the supremum over all signals that we can consider that have finite L2 mass, and we vary the domain U amongst a class of domains which have finite measure, right? So so our question is how large can this eigenvalue be? And of course, so this is, I just said it's an eigenvalue, and it's inspired, the notation is inspired by the Dirichlet eigenvalue, right? So this lambda 1 is the first eigenvalue of this operator here, which is called the localization operator. It basically localizes this time frequency representation of our signal to a fixed domain. And the heuristics is that, look, in the Dirichlet case, we know that information on the eigenvalues and eigenfunctions allows us to recover our domain if we know, in the most general cases, right? So it should be able to recover a domain if we're working with Laplacian, which is the most classical, one of the most classical operators in PDEs, then we should be able to recover our domain just from its eigenvalues and eigenfunctions. And the question is, well, can we get the same for this kind of operator here? And the issue is that operator is way worse than the Laplacian. So the Laplacian has this very nice way to compute it on a function. And if you want to take a look at that operator, this localization operator, well, first taking the short time Fourier transform is not trivial. Then you restrict it to a set. Then you take its adjoint at that guy. So this is this is not trivial at all in computational terms. So this is even more difficult than in the Laplacian case, where it's even not trivial already. There's just a couple of cases where it's known when the windows are Hermite functions, so very good L2 basis, or when our sets are disks, very, very good sets, right? And the hope is that, on the other hand, well, determining these values for general sets is very hard, but maybe if we want the best set, the set that maximizes this quantity here, then maybe that set is very nice, and maybe we can say something about that, right? So, for instance, in the case of the Dirichlet Laplacian, then there's this very famous inequality in geometric measure theory called the Faber-Cron inequality, which says that the first eigenvalue of the Laplacian, it's minimized by the eigenvalue corresponding to a disk with the same measure. Okay, and this only requires rearrangement methods, and we can actually describe the optimizer so we get a lower bound on this thing without the need for previous knowledge on our domains or previous knowledge on our functions, right? Okay, so indeed, confirming these heuristics, there is a result that I really like. It's from Fabio Nicola and Nicola-Tilli from 2021, in which the authors actually show, look, if you take a function to be a Gaussian, if you take our window function to be a Gaussian, which is normalized, then if our operator, if our short time Fourier transform of our signal localizes very well at a given domain, then the measure of the domain is at least log of 1 over epsilon. So unlike the other cases, in the other cases that we had that the measure of u when we take epsilon to 0 was converging to a constant. Now we have that the measure of u is blowing up. So this is a huge improvement in comparison to the previous easier uncertain principles that we had. And so in other words, and inequality holds if and only if this guy is a ball. In other words, this eigenvalue, it's maximized for the case of a ball of same radius as that. So we have this kind of inverted Faber-Cron inequality, which I think it's really cute. And I wanted to tell you guys a bit about the proof of that result and maybe my contribution after that. But first, let's talk about what's special about Gaussians. And I'm not sure whether there's anyone that does, there's people that do probability here, so they might tell me, well, what are you talking about? It's obvious what's so nice about Gaussians. Yeah, I know. But in this case, it is related, but in a very kind of distant way, right? So let's take a look what Gaussians give us in this problem. And what they give us in this problem is actually analyticity. So if we take the short time Fourier transform that I defined before, and I apply it with a Gaussian window, then what I get is an analytic function, which is what we call the Bargmann transform of our signal. So this is analytic, this is an entire function, times this two-dimensional Gaussian, times a harmless phase parameter. Since we want to know how this guy concentrates, this guy vanishes in absolute value, so we don't have to care about that. So Gaussians in this case, so they're giving us analyticity for free. We're connecting our, a priori very weird world of arbitrary signals to complex analysis all of a sudden, right? And so for that reason, this transform is special in the case when the window is a Gaussian. This is the Gabor transform. And from an applied perspective, more or less, the Gaussian localizes very well while being also very smooth, right? So the Hardy's uncertain principle, which is an uncertain principle in Fourier analysis, says that the Gaussian is the best object that localizes very much on space and very much on frequency, right? So this is kind of not by chance that this operator is so nice. It's invariant under the Fourier transform, this function. It localizes perhaps in the best way possible. So it should be expected that the Gaussians are somewhat nice to work with as windows. Okay, so let's maybe see how we prove the Nicola-Tilli result if we look through the lenses of these transforms, right? So actually, if we just translate it to a different context, we get that the Nicola-Tilli result is equivalent to this, what's on the screen, where actually I need to define this F2 space. So this F2 space is just the space of F, which are entire such that the integral of f of z squared e to the minus pi z squared is finite. And this is the norm of f in this space, squared. Okay, so we forget about the original problem, we forget about how two functions, and we look at analytic functions. And we want to look at this, all these analytic functions like that, and we want to say that for any analytic function that satisfies, that is in that space on the blackboard, then actually this inequality holds. With equality if and only if the set U is a ball, and the function itself is like, well, it's an exponential, right? So this, you can think of z naught equals 0, so this would be a constant. Okay, so this is a very nice, very cute inequality. Let's maybe see how we prove that, right? Okay, so the proof of that is, I think, extremely, extremely cute, and I hope you guys are going to agree with me. So we start with an arbitrary function in this space. Then we take this function u, which is exactly what's being integrated there in the norm. And we define this I of s operator, which is basically measuring how much this function f is concentrating on a certain set u, in a certain set where u greater than u star of s. So u star is just like a rearrangement of our function. It doesn't really matter for us, except for the fact that this u star has some very nice properties that this set here has the same measure, has measure s, right? So these are level sets of our function u. We're choosing u star of s such that the level set where u is greater than u star of s has measure s, right? So this function is very nice. We can use it, several properties of that. And in particular, we can see that this integral is less than that, just by an argument of like, if not, then we transfer mass from outside to inside, and we can compensate for that, right? So it's kind of a, I won't have time to give the full proof of this step in details, but it's a, kind of a transport of mass proof here. Okay, so instead of working with arbitrary sets, what we did already was get rid of arbitrary sets and work with our function only, right? So we're working at a function, and we're working actually with just this function I of s that depends on function f. And we need to prove that for each parameter s, this satisfies this, right? Okay, so it's just a one-dimensional inequality. How hard could it be? Yeah, so let's start to take a look at the proof of that inequality. So yeah, this should be step one, sorry. So if you take this function and we change variables slightly, and we take a look at this function g of sigma, which is I at minus log of sigma, right? So we just, instead of working with s that goes from 0 to infinity, we work with sigma that goes from 0 to 1, right? What are the properties of this new function g of sigma? So, well, the function g of sigma satisfies that, we draw a picture here. G of sigma at 1, g of 1 is I of 0, which is just the integral of our function u over the level set where u is greater than u star of 0. But this level set has to have measure 0 by definition. So we're integrating something against on a 0 measure set. So this has to be 0, right? So g of 1, it gets this value here. So we know this value of g. But g of 0, well, this is the limit where s goes to infinity of I of s. And this set just becomes the whole space when s goes to infinity. So we're integrating this function u, which is this thing over the whole space. And this becomes just the norm, this norm here, this norm here, squared, which we could, in the beginning of it all, we could have set to be 1. So we get 1 again here. Right? So our function g connects those 2 points in a suitable way. And if you look at this right-hand side here, under this minus log of sigma change of variables, we're going to see that this 1 minus e to the minus s gets transformed to this function here, to this straight line between these 2 points, right? And what we need to show is that the function g lies below that line. So if you want to show that this function g lies below that line, we know that it matches on both points. Well, I think it's a rather intuitive idea that we should try to prove that this function g is convex, right? So it matches at both points. Maybe it does something like this. And this is exactly what we're going to prove. So that this function g does something like this, that it's convex. And how are we going to prove that? So let me just write it explicitly. So this is the function g. So explicitly, if we differentiate and we use those properties of those rearrangements that we were looking at before, we're going to see that the derivative of g is given by minus 1 over sigma, the derivative of the I function, and the second derivative is given by this. So our function is convex if and only if its second derivative is positive, which is equivalent to this function I satisfying this inequality, right? So then we go further with that, and we look at, well, what are these two objects, right? So this first object is the rearrangement, u star, by just a co-area formula argument. And this second object here, well, it is slightly more annoying to compute, but if we use the co-area formula again, it's exactly this thing. Okay, so now we need to do something in order to prove that inequality there. And what do we start doing? Well, we start using what we have at hand, right? So let's maybe look at these level sets. So they appear in this definition, so maybe it's a good idea to look at those level sets. If we look at them and use Cauchy-Schwarz, we get this inequality, harmless inequality. And this is exactly equal to minus I double prime to the minus 1 times this thing here. On the other hand, we can use the isoperimetric inequality in this thing. It's just a boundary of a region, right? So we can bound this from below by the isoperimetric inequality, by the region that it encloses, by the volume of the region that it encloses, so we get an inequality like this. Okay, so we got that inequality, all is well and good. Now, well, we have this guy here, and we have this guy. This guy, we actually know what it is. We defined this measure of this set to be S, so that is cool. So we just need to compute this guy on the right-hand side, and that's where the magic of analytic functions comes in. So we want to work with this guy, but this is the same as working with this times t, right? But this is gradient of u modulus divided by u, which on the other hand can be written in this form. Then we can use the divergence theorem to write it. We can write it explicitly like this. And we can use the divergence theorem to write it as an integral not on the boundary, but inside the domain. If we integrate it inside the domain instead, then we get exactly this integral right here. But our function u, the nice fact that we have about our function u, is that the log of u of z, this was log of modulus of f squared minus pi z squared. And we're taking this function here, and we're taking Laplacian of that. So whenever a function, an analytic function, does not vanish, the log of its modulus is a harmonic. So when you take Laplacian of that thing, the only thing that remains is the Laplacian of minus pi times z squared. And the Laplacian of that is minus 4 pi. So we're integrating a constant over this set, and this whole thing just becomes this thing. And this comes exactly from the fact that we're working with analytic functions. Otherwise, this wouldn't have been possible. Okay? So what we get is that this whole integral, well, it's just an integral like this, but times u star, equals this. So we have that this right-hand side has this rather explicit forms. Well, we can cancel out both of these terms. This is I double prime to the minus 1, and this is I prime, as I said before. So if we rearrange, we get that I double prime plus I prime is greater than or equal to 0. And by this kind of magic of, well, you know, the analytic functions allow us to induce so much cancellation that even if I take their absolute values, I still have cancellation, then I get the theorem, and that's it, right? So in the final couple of minutes of this talk, I would like to maybe talk about my contribution. My contribution to this subject, well, one of the couple of papers that I have in this topic is recently to try to address the question of stability, right? So basically, well, we said that we characterized how much we can concentrate in a domain, and we said that the best possible is the ball, but it could be the case that we're achieving this upper bound that we have for domains that really do not look like a ball, right? So it's a natural question, even for applications, like maybe we can concentrate in an almost optimal manner if we're very far from the ball, right? So how much must we actually be close to the ball? And the theorem that it's a result by myself together with Jaime Gomez, André Guerra, and Nicola-Tilli from the last year, it exactly says that, well, if we're in the case that we almost concentrate on a ball, then the distance of our signal to the space of Gaussians is explicitly quantified by this, but not only that, well, this exponent 1/2 is sharp. You cannot do any better than that. But this constant here is essentially sharp as well. So this e to the measure of u, you cannot do better than that in the sense that you cannot put anything other than a polynomial in the dependence of u in terms of an improvement to that, right? And this is basically our contribution from last year. And the proof, well, it would be very technical. I figured I'd show you guys the nice part and sweep maybe the nasty bits under the rug. If you're interested, you can take a look, or I can discuss with you gladly later. But the sketch of proof is, well, just like before, we translate everything to analytic functions. We must prove to the function f in this Bargmann-Fock space is close to a constant in this case. And by the same reductions as before, we work with these sets of this level sets, right? But then right now, well, we're doing it in a two-step process, right? So first we show that if a function like that almost satisfies if a function satisfies this almost equality, then actually its supremum t has to be very close to 1. That's the first part we show. And then the second part that we show is that if the supremum is very close to 1, then the function is very close to a constant, right? So it's very easy to say that, but it's in the latter part, indeed, is actually as easy to prove as it is to say that. So if the supremum of a function like that is close to 1, then the function has to be close to 1 as well. But the first part, well, that's where the problems lie. So we need to show that the supremum is close to 1 if our function is close to satisfying that inequality. And the way we did it was, well, instead of looking at our function itself, we maybe should look at the rearrangement. And if we look at the original Nicola-Tilli proof, we get an inequality like this for free, which basically, well, now instead of bounding this guy by this constant here, we should just bound 1 minus t by this constant here. We should just compare it to the rearranged version. And that is really where the meat is, right? So that is the part that is more technically intricate, but also the part that is worth taking a look at in our paper is where, like, in order to obtain these results, we needed like some novel level set estimates for the concentration of analytic functions on level sets. And in order to do that, so just just as a last comment, so this is actually directly related to several things in calculus of variations. So just like a domain derivatives and so on. But it again, this part, unfortunately, I cannot show it in detail. But this part hides a lot of the places where analyticity was crucial. So the cancellation that an analytic function induced us before through the Laplacian of those guys, they appear here as well, such that even if we take modulus of analytic functions, we get something with incredible cancellation. And that's basically the gist of this calculus of variation proof that I have right at the end. And yeah, so before I finish, I'd like to comment on some open directions. So some open directions that I think are very much worth pursuing was, well, what can be said? So I discussed with you guys today about the maximizers of that problem. So what can be said about almost maximizer or local maximizers, or almost local maximizers to that problem, right? So what if I just, like in a certain sense, I just satisfied that this maximization locally? Can I say something about the function being a Gaussian or a disk? The second is, of those localization operators that I was telling you that taking a look at their eigenfunctions is weird, well, can we say something, can we construct, if we fix a function, can we construct a domain that has this function as an eigenfunction? As far as I know, this is only known in very particular cases. And I think like the most interesting question is maybe making rigorous that result by Jamon that I was mentioning before, that this guy here cannot concentrate perfectly on any set, or even nearly perfectly cannot concentrate on any set for more general windows, right? So recall that this latter part of our discussion was just for Gaussians. So if we take general windows, what can we do? And this is, so these are three of the many problems that I think are worth pursuing in this area. And yeah, so I think this is maybe concludes it. And yeah, so I'd like to thank you guys for the attention. And well, maybe hopefully I managed to convince that guy that he was wrong about engineering and mathematics. So happy birthday, Dad.